Welcome to lecture series of Robotics and Automation, Sri Ramakrishna Engineering College. I am Hemlata. I am taking today's topic is single phase half wave thyristor converter with a resistive load. It is a very most important topic in power electronics because it is especially used in many fields like in electrical drives, industrial automation and renewable energy system, where controlled DC power is needed from an AC supply. The circuit diagram for a single phase half wave controlled rectifier with a resistive load is shown in the figure. A single phase half wave controlled rectifier circuit consists of SCR or thyristor and AC voltage source and a load. The circuit is energized from a transformer secondary and an SCR is included between the load and the secondary. The AC input is given to the primary of the transformer. The thyristor is a unidirectional device allowing the flow of current only in one direction. When the thyristor is in forward bias, anode terminal is positive with respect to cathode terminal and the gate terminal is not triggered. There will be no conduction due to the reverse biasing of the inner junction of the SCR. Hence, the entire supply appears across the SCR. If the gate terminal of SCR is triggered with an adequate duration pulse, then the width of the depletion layer, that is reverse biased inner junction, starts reducing and finally disappears and SCR starts conducting. As soon as the conduction starts, the voltage across SCR drops to very small value and the supply voltage appears across the load. So the magnitude of the conduction current depends upon the instant where it is triggered, that is the firing angle alpha and the load resistance R. Since the circuit does not contain any energy storing elements, so the load current will be in phase with the voltage and becomes zero instantaneously with the voltage at zero crossing. See here, that means at omega t, that is pi radians per second. So during the positive half cycle, SCR is turned on. So we are getting the pulse after giving the gate pulse. If it is, for example, if alpha may be any degree, that is 30 degree, 15 degree or anything else. So during the negative half cycle of the supply voltage, the SCR is reverse biased. So there will be no conduction if the gate is triggered. See the V0. So only positive half cycle only we get the output. In the negative half cycle there is no output. The output voltage and current is also 0. So the load current and voltage are 0 from 0 to alpha when the SCR is triggered by giving a gate signal at alpha. The entire supply voltage except for drop across SCR will be applied across the load, that is from omega t is alpha to pi. So if at omega t is equal to pi, the phase reversal takes place and the negative half cycle of the input supply will start. So due to the negative half cycle, the SCR will be a reverse biased and it will be turned off at omega t equal to pi. So from omega t is equal to pi to 2 pi, the load current and voltage will be 0. So again when the positive cycle starts, that is omega t is equal to 2 pi, SCR will be forward bias but it will not be switched on until it is triggered. That is if omega t is equal to 2 pi plus alpha. See the diagram. Next we calculate the average load voltage and current with the R load. See, before going to is the definition for delay angle or firing angle. If a gate signal is applied to the SCR at omega t equal to alpha, where alpha is the delay angle or firing angle or triggering angle. So next we derive the average DC output voltage and the output current across the load resistance. So VDC is equal to V0, that is given by 1 by 2 pi integral of alpha to pi Vm sin omega t into d omega t. So we integrate Vm sin omega t and substitute the limit alpha to pi. So here in this equation Vm is equal to constant, so take outside. So integrate sin omega t, we get the minus cos omega t. So finally after substituting the limits we get the Vm by 2 pi into 1 plus cos alpha. Same way next we calculate the IDC, that is equal to VDC by R. So already we find the value of VDC, that is Vm by 2 pi 1 plus cos alpha. So IDC is equal to Vm 1 plus cos alpha divided by 2 pi into R. So next we find the RMS voltage across the resistor and the RMS current are computed from VRMS is equal to, that is RMS means root mean square value. So root 1 by 2 pi integral of 0 to 2 pi V naught squared omega t d omega t. So here in this equation Vm is also constant to take outside. So by using trigonometric equation, that is sin omega t is equal to 1 minus cos square theta. So from this one we find the value of Vrms is equal to Vm by 2 integral of 1 minus alpha by pi plus sin 2 alpha by 2 pi. So finally we got, after simplification, finally we got Vrms is equal to Vm by 2 integral of 1 by pi into pi minus alpha plus 2 alpha by 2. Same way we are finding the IRMS value, that is equal to Vrms divided by R, that is Vm divided by 2R. Already we find the value of Vrm, substitute here. So Vm by 2 pi root of 1 by pi minus alpha plus sin 2 alpha by 2. So the power observed by the resistor is PAC, that is equal to Vrms square divided by R. So therefore from the above equation we find the average output voltage and RMS output voltage, average current and RMS current, power observed by the resistor. Single phase half wave converter play a crucial role in converting AC to DC with the precise control. By simply adjusting the firing angle of the thyristor, we gain the full control over the output power, making this converter indispensable various industrial and domestic applications. So thank you all for your attention. I hope this gave you a clear understanding of the single phase half wave converter, not just how it works but why it matters. Thank you.